Okay, we are into chapter 4, and this is just a quick overview, hopefully quick. You might not think so, but we want to look at a quick overview. So what's happening is in chapter 3, so it's very important, I think, to keep kind of going back and looking at what we've accomplished or what we've done, and then comparing the new stuff. So in chapter 3, we looked at a single proportion, and with that we had a hypothesis test. So we had a H0 where P is equal to some P0, and an HA where that proportion was not equal to that P0. And so we looked at that hypothesis test, and related to that we looked at a confidence interval. Okay, now in this chapter, by comparison, now I think I kept mentioning in chapter 3 when we talked about a proportion, it's really an average. So in chapter 4, what we do is we look at, instead of a single proportion, we're going to look at a single mean. And so now we're just looking at more general averages. So again, a proportion is an average because we take the number of successes divided by the total number of trials, and in essence we're saying, well, we got a bunch of ones and zeros and we're going to take the average of that. Okay, so proportions really are averages, but generally speaking, averages are broader than just proportions. So in chapter 4, they start with a single mean and a very similar set of hypothesis, test a hypothesis and confidence interval. So we have a mu equals some mu0, where that's the sample, or sorry, the population mean is what we're asking about, and then we'll have mu not equal to mu0, and we'll have a confidence interval for a mean. So we go out, we collect some data, we take the average. Well, what do we think the bounds are on where that average really might be? And so that's how chapter 4 starts, and then immediately then following in chapter 3, they went to looking at two variables based on proportions. So they were count data. Okay, so this was count data. And the reason we had count data was that both variables, so come back over here, both variables were categorical. Okay, and so in looking at the two variables in count data, we went to the the chi-square test of independence. So again, up here for single proportions, actually I should point out that this was what we could use for all of these, no matter what, no matter how many aspects of the proportions we had, if we were looking at that target. we had a chi-square goodness of fit. Now, we also had other tests we could have run, but that was chi-square goodness of fit. And here, what we're going to use is a t-test, is what it's called. Okay. Now, in Chapter 3, when we went to two variables, and both were categorical, we ended up with this chi-square test of independence. And, you know, specifically, it was looking at how the proportions, the relative proportions were from column to column. Okay, now we could use row to row, but I'm going to say column to column. So it wanted to look at those relative proportions from column to column. Okay, so proportions from column to column. And so, in this case, we looked at those two variables, and we decided, from the technical part of the test itself, we looked at those proportions, but then we asked just, hey, was there dependence or independence between those two variables? Okay, so in Chapter 4, now, when we go to two variables, and we want to ask those kinds of questions about dependence and independence, this time, it's not count data. What happens is that we have categorical explanatory variables Okay, so categorical explanatory variables, but now we have numerical response variables. So that's the big difference is, you know, what do your data look like? Okay, so, and in this case, we're going to use, now we could use, again, a t-test of, for 2 columns, and that's entered, you know, that's in the book and so forth. But we're going to use mostly, and oops, I started to write the one and the other, analysis. Oops, analysis of variance test. Okay, now it's usually referred to as an Anova, and we'll use that whenever we're looking at 2 variables. And in its case, this Anova test, instead of looking at the relative proportions from column to column, again, remember, a proportion is really just a mean. This is going to compare means from column to column. So typically, our data in this case for our 2 variables, I don't know, I tend to like to use things like fertilizers or diets or something like that. So, you know, actually, I worked with a food scientist once, and he was publishing things on diets. and growth in Weanling. Ooh, good question. I don't remember if that's 2 E's or I'm going to have to look really quick here because I don't remember if that's 2 E's or an E and an A. I'm looking. Yeah, so it is in Weanling rats. Now, just as a quick aside, it's kind of interesting. I got in Weanlin, that far into Google, and the 1, 2, 3, 4, 5, sixth line down on suggestions was Weanling rats. How about that? Diets and growth in weanling rats, and so the idea being, can you optimize a diet or can you find the best diet? And so if you were looking at data like this, you would probably see something like diet 1, diet 2, diet 3, that kind of thing. So those would be our different categories for the explanatory variable diet. But then the growth, it would probably be weight gained or something like that at 1 week, at 2 weeks, at 3 weeks, and so this, for each of those diets, it might be some number of ounces, and I don't remember what those kinds of numbers would be, but like 4, 6, 4.2, 3.9, and this diet, maybe it was less, maybe it was like 3 and 2 and 5 and 2.4, something like that. And who knows, these numbers might have been, just to show that we don't have to have the same number of observations in each one of these, we'll have a 7 there, why not? And then here, we could have like, a 6 and a 8 and a 4 and 3 and 9 and 7, something like that. So your data would tend to look like that, and so you see we have our categorical variable here with its 3 different categories, but then these are all numerical down the columns. Okay, those are all numerical. And so what we would be doing is looking at the means of each of these and comparing those means and asking, in the case of an Anova, H0 would be that, I guess we'd have a mu1, a mu2, and a mu3 for each type of thing. So we're asking, would these means, does it look like the means here all came from the same population, or these data came from all the same populations with the same kind of means? And then the alternate is at least one is different. Okay, so that's where we're going in Chapter 4. Really mimicking or following the same kind of stuff we did in Chapter 3, but now the data are different. And that's it. The ideas of what we're trying to do are exactly the same. We would like to know if these diets impact the growth in some way. Could I use the diet to predict the growth? Now, more likely, you would like to say, does the diet cause the growth? But again, generally speaking, I haven't told you enough information to know if we could get any kind of causation here. But we could certainly at least get, determine dependency. And dependency, if they are dependent, if diet and growth are dependent, at the very least, I could use the diet to predict the growth. Okay, it may not be causing the growth. Now, it probably is, but we don't know. But I could use the diet to predict the growth, if nothing else, all right, with these averages. Okay, so that is an overview of Chapter 4.